Back from the break, and we're still talking about performance issues with CMOS devices. So we're going to really start talking about distributed RC effects. As you know, the performance of a simple or basically any gate is directly related to charging and discharging the load capacitance. This is typically through the resistance of the pull-up PMOS or pull-down NMOS transistors, and in many cases the channel resistance, which is the limiting factor for the resistance. So it provides the lion's share of the contribution to the resistance in the RC type of delay. But sometimes distributed resistances of a long line can't be neglected, and nor can they be treated as a lumped element. A lumped element just means that you treat it as a lump of R and a lump of C. So this typically leads to what you might call propagation of a signal along a long line. Propagation is in quotes because it's RC, and so it's not really propagation, but rather more of a diffusion kind of process. So it depends on distributed R and C along the line, and it also depends upon the source and terminating impedance, much like they would be boundary conditions for a diffusion problem. For long lines, distributed RC may dominate. That sort of points out, particularly if you're routing much on poly or diffusion, but you don't. So multiple metal levels have sort of circumvented that problem, but with the designer's insatiable appetite for speed and performance, distributed RC is still important. And here's sort of the schematic representation. We have a nice long metal line here divided into these sections of R and C, and this is our notation here. At this point here, the voltage is V sub J. We got some current going through this capacitor, we got some current flowing along the line through this resistor, and some current flowing this way. So it's a distributed RC line model. The R is in terms of ohms per meter, C is in ohms per meter, or farads per meter, and this just means it's per unit length. And what we're going to do is just write KCL at that node J. So we're just going to write KCL here saying, I of J minus 1 is equal to I of J plus I of C. So once we have that, we can express that in terms of the voltages and the resistances that we know, as well as the current flowing through that capacitor in terms of C dV dt. So the capacitance there is C delta X. Just like the resistance in those sections is R delta X, because those were per unit length, as you recall. So we just combine that, writing KCL at that point, and we see we have this equation, which is a difference equation, and it's going to lead us to our differential equation. So this is like an in-class assignment surprise, if you like. I don't know why I call it that, but you go from the difference equation to the differential equation on page 77 without too much effort and maybe a little bit of hand waving. But before that, I wanted to do a little diffusion illustration. This is this Obama here with an opportunity to make decisions to the right or to the left with probabilities p and 1 minus p respectively. And he starts out at x equal to 0. And what we're interested in is f, which is the probability that Obama will be at point x at point time t, and that's n steps later. So that's what we're interested in trying to derive. According to Bernoulli's formula, we're going to get a nice closed form expression for this. It's a binomial distribution. And more interestingly, for some of us anyway, when this evolution is expressed as a difference equation, it's simply restated here in terms of a difference equation. You find in the limit you get what's called this Fokker-Planck equation for diffusion, which is going to look very similar to the equation we're going to get in a minute for our RC line. The important point here is we sort of got a physically meaningful result and are able to derive it, if you like, for a problem whose formulation was quite artificial, and sort of adds some street credibility to the difference equation approach that we just looked at for the distributed RC line. So as the number of sections tends to infinity, the sections become very small. This reduces the expression to the well-known diffusion equation rather, from our difference equation. And the way you come about thinking of that is, if you look back here, we have on this side the C dV dt, so we can throw this delta x down here, we can get delta x squared down here, and on this side we get a difference of differences. So that's going to give us a second derivative, and that's going to give us a first derivative. So quite easy for us to get to this equation. Solving it's another thing, but I'm not going to worry about that here. We know that we could derive this diffusion equation. It looks like diffusion, and we can look up what its solutions happen to be. And there are a number of techniques for doing that, of course. But the solution is of this form, where Tx is proportional to x squared. And what that basically means is that that we're going to end up with a quadratic increase in delay as the length of the line doubles. And here's a simple example. We have this line here, this length L. We sort of think of the resistance as being equal to R times L. We think of the capacitance as being equal to capital C times L, because those were per unit length. So our delay is going to be something on the order of RC, which gives us this L squared term here. If we double the length, well, the length becomes 2L. The resistance now is R2L. The capacitance is C2L. And the delay, again, being proportional to RC, is going to have gone up by a factor of 4 when we double the length. So the important point is the length doubles, the delay quadruples. So you get a quadratic increase in delay with distance, and that may dominate performance clearly if the line is long. Number of circumvention strategies, dividing the line up and inserting buffers. We saw that very early on when we talked about problems associated with the clock tree synthesis. And if you want to see some interesting approaches, that's a very good place to look. The best theoretical improvements might be to reduce that delay from a quadratic to something which is logarithmic, but still becomes a function of distance. At gigahertz frequencies, might point out that inductances could also play a role, and many of these may be sort of lumped at the package lead instances, but they could still be an issue on chip as well. So anyway, getting back to our distributed RC, the discussion, like I said, is a bit leading. It's not a propagation, it's a distributed RC line model, and it corresponds to the diffusion equation. We're anticipating distance to cause a doubling of distance, cause a quadruple delay. The important points here: it does not support a propagating wave, so it's sort of something that is associated with a point on this type of graph here, where we'd maybe arbitrarily set it to be 63% of VDD. So this would be as if you were driving a distributed RC line. It tends to fill up in this fashion. As you can see, it's not propagating, but it's this point here that you'd say is looking like it's got the characteristics of delay quadrupling when you double distance. So in this particular case, you double the distance from here. You went from time t equal 1 to time t equal 4. So it fills up more like syrup in a bathtub. Not that I've ever tried that. Often treated or modeled as delay. That this says I'm taking this R total, the C total, I'm assigning it some type of delay. It's certainly better than doing nothing, but that wouldn't be very accurate. We will return to more accurate delay models later, and some tools that are available to get a better, better simulation of what's actually happening, as well as some pedagogical tools that help us see what happens when we get into a mode where we look at something that looks more like a transmission line. Some of the other complications, of course, is that simple little blue line from a few slides back wouldn't look like that at all. The traces tend to be fairly complicated. They have lots of transitions and lots of layer changes, so each of these cause mismatches, and the resistance per unit length, capacitance per unit length, everything is going to change, and would definitely complicate the an analytic kind of expression for the delay, but certainly you'd be able to simulate that with reasonable EM packages. And that brings us to another break.